We're in the midst of a climate crisis. In response, countries are pledging significant action to reduce their carbon emissions. The European Union intends to be carbon neutral by 2050, for example, and China by 2060. The Paris Climate Agreement was adopted by almost 200 parties in 2015, obliging countries to set out their plans to reduce greenhouse emissions in increasingly ambitious 5-year cycles. And carbon consciousness has also made its way into corporate culture, with organisations like BASF aiming for carbon neutral growth by 2030 and General Motors aiming for 2040. When discussing large-scale carbon reduction, the focus is often on power generation, replacing fossil fuels with solar, wind or tidal, for example, or on new technologies like carbon capture and storage. But for a truly sustainable future, we need a wider view.
I'm Chris Stumpf, and I work at Waters Corporation. I'm a senior manager, and I focus on market development, and really what I've been looking at pretty extensively as of late is the area of electronics and also sustainability. And I've kind of developed the title of the Green Ambassador within the company because I'm tying in a lot of the electronics, especially the lithium-ion batteries, because it connects into carbon neutrality, but also it connects into supporting sustainability goals of a lot of corporations and also a lot of countries around the world as they're trying to meet their carbon neutrality stated goals.
Waters Corporation is the world's leading specialty measurement company. They don't make lithium-ion batteries or research new sustainable materials themselves, but they develop chromatography, mass spectrometry, and thermal analysis techniques that enable scientists and industry worldwide to answer cutting-edge questions.
I think there is a common thread with this, and I think a lot of this is really accelerated due to COVID-19. And what we've kind of discovered is that the supply chains are being disrupted, and there's this need to be able to manufacture within countries and things like that. But a lot of the supply chain, as it stands now, is not kind of sustainable. So the ways of kind of reducing that are to use 5G, which enables the Internet of Things, which enables automated manufacturing. And also there's artificial intelligence, which can be focused directly on managing specific aspects of the supply chain and continuous manufacturing, things like that. But then the third thing is really the underlying technology for a lot of that is energy, and basically how do you store energy and use energy where it needs to be used. And one way to do that is with batteries, and specifically with lithium-ion batteries. They're the dominant battery type today, and they enable the electric cars, they enable the hybrid electric cars, and also they're used in the electric grid for smart grids. Their use is going to be very pervasive across the landscape. In addition, they're heavily used in consumer electronics, our smartphones and our laptops and all these types of devices that we use nowadays.
While all of these technologies do play a role in fostering development and reducing our reliance on outdated infrastructure, batteries perhaps seem the least exciting of the lot. It's only about 30 years since the first commercial lithium-ion battery, but in that time they've become ubiquitous, commonplace, even forgettable.
The AI and the 5G, they receive a lot of publicity. I mean, they're even in like pop culture. You could think about Stephen King's novel, The Cell, kind of based on like creating zombies with cell phone towers and things like that. And then I think Steven Spielberg had a movie in 2001 based on artificial intelligence and creating like a human person. But right now, what we basically have is this, I guess, taking for granted this lithium-ion battery technology. It's everywhere. It's in our laptops. It's in our cell phones, and there's still a lot to be done. So the Nobel Prize winners in 2019 for the Nobel Prize in chemistry, Goodenough, Whittingham, and Yoshino-san, They said that there are 6 things that still need to be done with regards to research: reducing the cost, improving the safety, increasing the charge density. For example, if you're going to put these lithium-ion batteries in an airplane, or you're going to put them in a big tractor trailer truck or something like that, you need a lot more energy density. And then there's the idea that is the lithium-ion battery technology as it's being practiced today with the liquid electrolyte fluid and the cathode and the anode, is that the right approach? Or do we go with another type of technology? Do we use solid state, for example? Or do we replace the electrodes with other types of technology? For example, the lithium and the cobalt that are in the anode and the cathode are not really that sustainable. So supply chains and extracting that, it's a bit difficult to justify this from a sustainability perspective. And could you perhaps replace some of that with more common metals like sodium or something like that? So there's really a lot of opportunity here for really basic R&D, just to kind of decide which direction we go and which is the most commercially viable option.
Sustainability means different things to different people. For a business strategy to be sustainable, it needs to ensure profits are greater than costs. But this can conflict with the environmental bottom line, ensuring no environmental or ecological damage to sustain the natural world for future generations. Taking a global view, the United Nations has set out 17 Sustainable Development Goals, which include affordable and clean energy, climate action, and responsible consumption and production, alongside gender equality, sanitation, peace, and justice.
In addition to a clean environment, they also want to promote civil stability, because they want to minimize this extreme wealth inequality, basically reduce the possibilities of war and things like that. So with regards to, lithium-ion batteries, being within that framework of sustainability and trying to source your materials plays a little bit of part into that kind of 17 development goals of the United Nations. So if we think about the Paris Climate Treaty, if we can maintain our carbon emissions to like 1990 levels, then we can arrest the increase in the Earth's temperature. Basically, that justifies the investment in all this R&D for the lithium-ion battery and all the products that it's going into. Yoshino-san talked about lithium-ion batteries kind of being the bedrock of the sustainable society. But there's other things that we don't quite realize until we get to that world of having a lot of our consumer electronics and our cars and our airplanes and things like that running on lithium-ion batteries or another alternative to lithium-ion batteries. It's an enabling technology. It's playing a small part in this overall scheme of sustainability. It's not the only thing that's going to help with this, because it's kind of a hybrid situation where we have lots of things that we need to do in order to reach a sustainable future. But it's kind of the foundation of that, in my opinion.
If batteries are to be the bedrock of a sustainable society, it's vital that we understand how to tailor them to specific uses. The battery in your laptop has a very different specification to the ones in the latest electric cars. This is where measurement technologies come into their own, helping with everything from blue skies research to efficient manufacture.
Hi, my name is Neil Tamars. I am a product manager for our microcalorimetry products. These are products that are used for specifically investigation of battery research and development. So batteries are, because it's a contained, non-moving, you can think of it as a machine almost. It's like a complex device. There's not a lot of techniques that can be used to study whole cell batteries. A lot of them are destructive techniques. Having a test that you can use to then either look at the chemicals separately, but also look at whole cell batteries is important. So that's where calorimetry really has a very important contribution to the research field. Another thing, researchers are also starting to look at bringing in some of the tools that chemists or pharmaceutical sciences are using because of the sensitivity. So HPLC and mass spectrometry, there's also cryo-EM. That's another technique that's historically used just in protein science. Now it's being kind of carried over into material characterization for batteries. As the batteries change and the performance demands accelerate, that's where they're drawing in some of these tools that wouldn't traditionally be used by chemical engineers or chemists. There's not a one-size-fits-all battery, and so there's going to be a lot of research to determine how best to build certain batteries for certain applications.
You can think about safety and maybe energy density or something like that. So in order to think about that as far as an analytical characterization perspective, you have to go back and think about the battery itself. There's four primary things that you have to think about when you think about a battery. So there's the anode and the cathode, and we're all familiar a lot of times with our own batteries. We'll see the terminals of the batteries, though that is basically the anode and the cathode. Inside there is the electrolytes, and so there's additives and all this kind of stuff. And that is put in there partly to enhance the performance of the battery, but it's also put in there to kind of suppress potential fires and things like that. And then on the inside, there is actually a polymer separator. Its purpose is basically to prevent a short circuit between the anode and cathode. If you actually have a short circuit, so if that little polymer gets punctured or if it shrinks, the battery gets hot very quickly. And so if the battery gets hot very quickly, it can cascade, because a lot of times these cars will have thousands of these batteries in a battery pack. And it can cascade like dominoes.
So the calorimetry can tell you how fast the reaction's happening, how much of the reaction's happening, even the fact that there is a reaction happening. So a researcher might have some structural data of a picture of their material, their chemistry, if they were to cut open a battery or before it even gets into the battery. The calorimetry tells you how do all those components together react. Are there reactions in there that we don't want? We're measuring heat. Do those reactions get too hot? The chemistry that goes in the battery is going to help the charge density. It's going to help the battery life cycle. Safety is also something that can be looked on early on in the R&D process of make sure that chemicals are compatible. High precision coulometry is another technique that's paired with calorimetry to understand these parasitic reactions. These are the small, minute reactions that researchers want to understand, because it points directly to how good their battery is going to be.
But you also got the capabilities of really understanding the chemistry that's going on and all these side reactions. And these side reactions basically rob the battery of its main goodness, the power that it's generating. And so if you can understand that from a molecular perspective with techniques such as mass spectrometry, or maybe the whole battery itself, battery calorimetry, then you can really get to understand how you can actually maybe make this battery last 20 years, 40 years, 100 years.
Fine-tuning the chemistry within a battery isn't enough to make a perfect product. The right battery case is essential to allowing that chemistry to work in situ. To confirm a case won't collapse in the real world, researchers use techniques like thermogravimetric analysis, or TGA. By applying heat to a material in a controlled way, they can precisely measure not just physical deformation, but chemical changes that would indicate degradation or oxidation.
So the casing is actually very important. So the polymer that it's made out of, if a car runs into something and it impacts and kind of crushes that casing, well, you'd like to actually make a casing that's kind of somewhat resistant to that. So if you can design a casing and use analytical characterization in order to build that polymer so that it resists that, and also the electrolyte on the inside, if you can put the right additives in there, that if the thing does start to heat up, it can trigger some type of flame repression. So there's a number of these things that you can do from an analytical perspective to kind of build a high-performing battery that has a lot of the energy performance that you want. But at the same time, you got to think about the safety perspectives as well.
One essential component of a sustainable future, highlighted by the United Nations goal of responsible consumption and production, centres around what happens to a product at the end of its useful life. Electronic waste is a growing problem. The UN estimated 50 million tonnes was reported in 2018, and levels are expected to double by 2050. This includes complex equipment that is hard to recycle and can contain components that are toxic or hard to replace, creating a vicious circle whereby materials are mined in environmentally damaging ways, only to be returned to landfill in just a few years. With batteries, as with other electronic components, research and characterization can help us to reduce, reuse, and recycle.
There's a lot of work going on into understanding recycling. I mean, Apple is one of the largest recyclers of batteries in the world. It's no surprise. They have batteries in all of their devices. I'm sure they want those back, and they have a process that they might be able to recycle some or all of the battery. There's lots of other techniques, but understanding how do you take something that's a static machine full of chemicals, how do you take it apart, how do you recycle these small little pieces? There's some initiatives or research that's just goes into like, we're going to grind up the battery and try to purify certain parts of it by just making it smaller and smaller and smaller mechanically. Others, open up a battery, extract certain materials. But I think it is a big challenge understanding how batteries are going to be recycled. What's the best way to do that? I don't think it necessarily fits our current recycling process, how we know it, of separate. It's easy to separate like trash. With batteries, it's a lot more complex.
Right now, there's regulations in order to collect these batteries because we don't want them to get in the waste stream. But as far as collecting enough material to reuse it, I think the amount of electric cars are actually not high enough to make that economically feasible. There's two major areas that people look at with regards to recycling the batteries. The first is relatively straightforward. You take maybe the battery pack from a car and you take it out of the car and it's in some type of a casing. You open that case up and there's all these individual battery cells. And you can test each one of those cells, and you can pull out the ones that are bad, and then you can replace them with good ones. And then you can repurpose that battery pack either by putting it back into another car, or you can put it into a smart grid. And maybe the smart grid's energy requirements are maybe not as aggressive as what the car is, so it actually might last a lot longer in the electric grid. So there's that. It basically is kind of a reconditioning of the battery. Then the second one is to take that battery pack out of the car and then, or the cell phone or whatever, and basically open up the battery pack, take out the cells, and then grind them up, and then try to separate things into cobalt, magnesium, lithium, and all this, and try to get back to virgin materials. And so that's another area where you need analytical characterization. You need mass spectrometry, NMR, TGA, DSC, all these types of techniques in order to just understand the physical property and the molecular properties of this and see if you've actually gotten yourself back to where you want to be.
Pure virgin materials have well understood properties, but when a material has been reclaimed from a disused battery, we need to be certain that it will behave in the same way when it returns to the manufacturing process. With many companies operating on a financial knife edge, the risks of using recycled or reclaimed materials that may contain impurities can be too much to bear.
Without the analytical characterization, without the molecular understanding of the anode and the cathode material and the electrolyte and the polymer materials that the battery cell is made out of, without that molecular understanding, and then also there's the physical understanding, with a TGA, you can actually take that polymer and you can melt it with a thermoplastic. You need to know when these polymers melt because that's part of the manufacturing process. You melt these polymers and then you blow mold them or you do different types of manufacturing with them. But you need to be able to understand that because if the temperature shifted somehow, then it's not going to work in the existing manufacturing process. So you're going to have to do all this adaptation. So really understanding, do I still have that same polymer or has it degraded somehow? If you take that polymer that say that was in a battery, maybe you use it in a different application, maybe using a car bumper. Well, if that polymer now is brittle and it's gonna break right away, it's not going to be a good application in a car, because you need that bumper to kind of resist that impact. So absolutely, analytical characterization across that whole, from the very beginning of making a battery to kind of the circular economy and reusing the components. You got to understand that from each step of that process.
So as we collectively try to find ways to adapt to a challenging future, to meet the ambitious targets that we set for our own differing versions of sustainability, it's essential that we use every tool available to us to probe, analyse and understand the technology that we take for granted. And with that understanding, we'll be able to build and rebuild better batteries that can realise Akira Yoshino's vision of them as the bedrock of a sustainable society. For more on this topic, check out Chemistry World's new sustainability collection, curated content created with our partners. You can find that at chemistryworld.com/sustainability. This podcast featured Chris Stumpf and Neil DeMars from Waters and was produced in partnership with Waters Corporation. I'm Ben Valsler from Chemistry World. Thank you for joining me.